Hey, we're going to talk about the chain rule, which is a way to take the derivative of composite functions. The rule is right here. Derivative of f of g of x, that's the notation for a composite function. You may also be familiar with the notation of f of g of x. That's the same thing as the composite function. Anyway, the derivative is the derivative of f with g in it, and then times the derivative of g. So you see f prime of g times g prime. Before we actually start working with the chain rule, let's make a couple things clear. Remember, we have function-specific rules. So when we go to take a derivative, usually we're looking at the type of function we have. So one of the rules we have is the power rule, where we might have something raised to a power, and in this case I have it written as x to the n. So if you have a variable raised to a power, derivative of the power rule is very straightforward. Derivative of x to the n is n times x to the n minus 1. Bring the power out front and reduce it. Down here, derivative of the exponential e to the x is e to the x. Now these rules are very specific. Okay, x is a variable. It could be y, it could be w or s or r, whatever. But it doesn't allow for things like 2x or x minus 7 or x squared. So in these cases where you see x with these introductory function-specific rules, power rule, exponential rule, so on, you are limited to a very specific function to work with here. Okay, so all of these you're looking at just x being a variable. And then we have the multifunction rules, which are what gives us a little bit more depth. The sum difference rule lets us add two functions together. And if we want to take the derivative of them, it's the same as taking their derivatives and adding them together. Okay, so as long as we know how to take the derivative of f and we know how to take the derivative of g, we can find the derivative of f plus g. So we could take the derivative of e to the x plus x squared, okay, instead of just having separate rules. Usually a lot in polynomials. Product rule, if we have two things multiplied together that we know how to take the derivative of, we can use the product rule. If we know how to take the if we know how to take the derivative of two things in a quotient, we can use the quotient rule. But in all those cases, we have to be able to break it down into something that will use a function-specific rule. So back to the chain rule. The chain rule, I said, will let us take the derivative of composite functions. But before we do that, let's remind ourselves what a composite function is. So composite functions let us place one function as the input into another function. So here I've got the example. F of x is natural log of x. So that's one of our functions. Okay? F of x is the natural log of x. And g of x is going to be 5x to the fourth. So that's two completely separate functions. We know how to take the derivative of each one separately. Okay? But before we go down chain rule, let's see what the composite functions look like. So over here we have f of g of x. Okay? So no matter what notation we use, what this means to us, if we can recall, is that we're going to take f, which was the natural log of x, but we're going to put something in it. So usually we like to put numbers in, but this time we're supposed to put a function in. So we're going to put in g. Well, our g function is 5x to the fourth. So I'm taking the g function and placing it into f. Okay, so g, which was 5x to the fourth, becomes the input of f, which is exactly what happens here. So that composite function f of g is natural log of 5x to the fourth. And be careful just to make sure we're okay here. If we want to do g of f, that means we'd be taking f of x and sticking it into g. So we could write down our g function, which is 5x to the fourth, but x is a input placeholder, so I'll leave a little space there, and I'm going to plug in natural log of x. So I stuck f into the g function. It became a input. So make sure you understand how composite functions work. Okay. So let's try and take the derivative of one of these. So we're going to do the derivative of natural log of 5x to the fourth. And we're going to use that long version of the chain rule. Okay, the derivative of f of g is f prime of g times g prime. So let's identify our parts. From the previous example we just did, we can tell that this was made up of f of x being the natural log of x. That's what's getting an input. And what is that input is g of x, the 5x to the fourth. Okay, so we stuck 5x to the fourth into natural log to create this function. So we understand what f and g are. So let's look over on the right hand side of the derivative rule and see what we need. We need f prime. So we've identified f to be natural log of x. F prime is 1 over x. So derivative of natural log of x is 1 over x. We're going to place g into that derivative. Now that's the original g. So I don't have to do that just yet, but let's just go ahead and do it. F prime of g of x will look like 1 over x is our placeholder, and we'll plug our g in, 5x to the fourth. Okay. So just making sure you understand where things came from. But we also need the derivative of g. So g was 5x to the fourth. Derivative of 5x to the fourth is 20x cubed. So we'll put this together. Our derivative of the natural log of 5x to the fourth will be f prime of g, which is 1 over 5x to the fourth, times g prime, which is 20x cubed. Okay, there's g prime, there's g prime, there's g prime. Okay, just making sure you understand where everything came from. So, seems like that can be cleaned up a good bit, right? So I could write it one over the other, 20x cubed over 5x to the fourth. If I want to clean that up, it'll be 4 over x. Now, I'm not saying that you're going to get nice, clean, simple derivatives every time you use the chain rule. This one just happened to work out pretty nicely. Okay, and we use the long composite definition here. All right, let's do another one. Hold on one second. Okay, I'm back. We're going to do another chain rule example using the composite notation here. And the function we're going to try and use is the quantity of 4x cubed minus 5x, and that's all going to be raised to the 8th power. Okay, so we got to figure out what's an f and a g if this works. So we don't want to take 4x cubed minus 5x and multiply it times itself 8 times. We could do that if we want to do a whole lot of algebra, but let's see if we can just do a little bit of algebra. So, main thing here is to figure out what's happening. So the main thing that's happening is this to the 8th power up here. Okay, I think that makes a good f. Okay, so let's just kind of see if that works out. If f of x is something to the 8th, because that's the last thing that's happening here. So something must be plugged in before you can do to the 8th. So let's just give it a placeholder. F of x will be x to the 8th. And then our g of x can be what's being raised to the 8th. Okay, so let's see here. G of x would be 4x cubed minus 5x. And we've taken something that would need a lot of algebra to figure out what it looks like as a polynomial and separate it into two simple things. So keep in mind, if I take the g, 4x cubed minus 5x, and plug it into f, I will get the original back, and that's what I should get. So I need some derivatives now. Okay, I need the derivative of f. Very simple. Derivative of x to the 8th is 8x to the 7th, and then I need to plug g in to that derivative. So it'll be 8 placeholder to the 7th, and what's going in that placeholder is 4x cubed minus 5x, or as we better know it as g. Plugging that g in. Okay. And we got to take the derivative of the g part, so g prime. Derivative of 4x cubed is 12x squared. Derivative of negative 5x is negative 5. So that is the g prime there. So let's put all that together. We came up with f prime of g to be 8 4x cubed minus 5x to the 7th, and that will be times g prime, which will be 12x squared minus 5. So here are the parts. There's g prime. There is the g that got placed into the f prime. Okay, you could technically try and distribute that 8 into the last part, but there's not much use in it unless you just really want to. So you can kind of tell that this takes a little bit of work and a lot of care. And the hard thing about the composite definition here, the long form that let's just work with any composite function, is that you have to be able to identify the f and the g, and you have to do it correctly, of course. And sometimes that can be kind of hard. So instead of always trying to just break it down to the f and the g, we're going to take a look at trying to relate this more to the function specific rules. Okay, so we'll save that for the next video.